From AGI to ASI, Pathways, Frictions, and the Future of Machine Intelligence Executive Summary. The transition from human-level artificial general intelligence (AGI) to artificial superintelligence (ASI) represents a continuum of machine intelligence that is increasingly moving from theoretical speculation to a concrete technological target. Current trends indicate an exponential growth in effective compute, a compounding metric of hardware improvements, increased investments, and algorithmic efficiency, estimated at approximately 10x per year. While AGI is defined as a system possessing median human-level intelligence, ASI is characterized as a system that far surpasses human collectives across virtually all tasks and domains. This briefing explores 4 primary pathways to achieving ASI: quantitative scaling of compute and data, algorithmic paradigm shifts, recursive self-improvement (RSI), and the emergence of group agency through multi-agent collectives. However, this trajectory faces significant frictions, including the exhaustion of high-quality human data, the data wall, the abstraction barrier, the inability to form novel concepts without grounded experience, and the increasing resource demands of advanced research. Achieving ASI may not be a single transformative step but rather a series of breakthroughs requiring a massively interdisciplinary global effort. 1. Characterizing the intelligence continuum. The report utilizes the Leg-Hutter score, a formalization of intelligence as average performance across all computable tasks, to ground the definitions of various intelligence levels. Level definition, scope AGI, human-level artificial general intelligence, roughly as intelligent as a single median human on most cognitive tasks. ASI, artificial general superintelligence, superhuman abilities across virtually all tasks, exceeds the performance of large, well-coordinated human expert collectives. Universal AI (UAI), the theoretical limit of intelligence defined via the AIXI agent, the incomputable endpoint that maximizes the Leg-Hutter score. The advantages of digital intelligence. Digital intelligence possesses fundamental properties that amplify with compute, creating a widening gap between biological and machine capabilities. Speed and scale. AI can ingest information, e.g., thousands of books, and produce outputs at bandwidths far exceeding human capabilities. Substrate independence. AI can transition between hardware, upgrade to more efficient computers, or run on distributed systems. Lossless replication. Unlike humans, AI can be perfectly copied, including its memory state, lifetime experience, allowing for backups and the spawning of millions of identical expert instances. High bandwidth sharing. Homogeneous AI instances can share raw learning signals, e.g., gradient updates or replayed experiences, bypassing the lossy compression of human language. 2. Technological pathways to superintelligence. 4 non-mutually exclusive pathways are identified for the transition from AGI to ASI. I-scaling compute, models, and data. This pathway relies on the bitter lesson, the observation that general methods leveraging compute and search consistently outperform human-authored heuristics. Growth rate. Effective compute is currently growing at an order of magnitude 10x per year. The theory. If search is at the heart of intelligence, quantitative scaling of compute may be sufficient to reach ASI, even if individual model intelligence plateaus. 2. Algorithmic paradigm shifts. As current transformer-based architectures hit limits, true paradigm shifts may emerge. Dynamic computation. Moving beyond fixed forward passes to tool-augmented planning and specialized external engines. Unbounded horizons. Replacing fixed context windows with linear time architectures, e.g., Mamba and retrieval integrated memory systems. World models. Learning compressed, manipulable representations to simulate futures and reason counterfactually. 3. Recursive self-improvement (RSI). RSI occurs when AI facilitates its own research and development, creating a positive feedback loop. Genotypic RSI. AI writing better code, architectures, and optimizers. Mimetic RSI. AI curating or generating higher quality synthetic data and distilling test time search AlphaZero style. Sociogenic RSI. Specialized agent collectives increasing efficiency through division of labor. IV. Multi-agent coordination and group agency. Superintelligence may emerge not from a single model, but from the orchestration of numerous agents. Virtual agent economies, using market dynamics and price signals to coordinate vast numbers of agents. Hyperspecialization, forming group agents, e.g., automated corporations with cognitive capabilities superior to any individual member. 3. Critical frictions and bottlenecks. The report identifies 6 primary breaks that could slow or halt the progression toward ASI. The data wall. Model size growth is outpacing the global production of novel human text. By the late 2020s, high-quality public data may be exhausted. Countermeasures, training on self-generated interaction data, high-fidelity simulations, and the distillation of test time scaling. The abstraction barrier. Current models excel at recombining human-generated concepts but may lack the ability to form novel conceptual primitives from raw data. The Einstein test. A system today likely could not derive general relativity from the same information available in 1900 without the pre-existing conceptual primitives calculus, causality provided in its training data. Research getting harder. Maintaining progress rates often requires exponential increases in inputs. The researcher gap. Keeping up Moore's law today requires approximately 18x more researchers than in the 1970s. The AI solution. If AI can automate research, the cognitive aspect of this bottleneck can be bypassed by simply scaling compute for artificial researchers. Economic and resource constraints. Scaling through multiple orders of magnitude requires massive investments in energy, rare earth materials, and gigawatt-scale infrastructure. Diminishing returns may make continued scaling economically unviable unless AI produces equivalent economic returns. The neural paradigm limit. Transformer-based predictors may be fundamentally limited by issues such as hallucinations, vulnerability to prompt overrides, and a lack of grounded world models. Deliberate slowdown and regulation. Societal backlash, safety concerns, or military, political, race dynamics may lead to regulatory caps or temporary moratoria on capability scaling. 4. Fundamental theoretical limitations. While ASI will be immensely capable, it is not omnipotent. It remains bound by established physical and logical constraints. Fundamental physics, the speed of light limits information propagation, the Landauer principle dictates the minimum energy for computation. Complexity theory, limits on practical computability P versus NP still apply, though ASI may use superior heuristics for approximate solutions. Real-time latency. Experiments in the physical world, e.g., biology, climate cannot be sped up arbitrarily, creating an embodied bottleneck. Epistemic uncertainty. Fundamental limits in observability and predictability prevent perfect control of complex dynamical systems. 5. Future outlook and research agenda. Preparing for a post-AGI world requires shifting focus to ASI-ready benchmarking and forecasting. Benchmarking ASI. Traditional human expert benchmarks GPQA, frontier math are saturating. New methodologies must include setter-solver, I approaches and general compression benchmarks. Multi-agent scaling laws. Research is needed to understand how collective intelligence improves as a function of agent population size and interaction density. Recursive improvement monitoring. Quantifying the extent to which AI systems are already facilitating hardware design and algorithmic discovery. Knowledge-seeking KS objectives. Exploring agents that maximize information gain rather than scalar rewards to mitigate reward hacking and delusion box scenarios. We can only see a short distance ahead, but we can see plenty there that needs to be done. Alan Turing, 1950.